Okay, going to be working on 12.2 now, which is the second derivative in the graphs. So we're going to start out here with number 17. And we're given a function. F of x is 2x cubed. 2x cubed minus 4x squared plus 5x minus 6. And we're asked to find this. So this notation means we need to take the derivative twice. So let me find the first derivative, and to do that I just use my power rule. So 3 comes out, it's 6x squared. Here the 2 comes out, becomes minus 8x. Then here the derivative of x is 1, so the 5 just comes down. So that's my first derivative. Now my second derivative is just the derivative of this. So same rules, 2 comes out, we get 12x. Derivative of that is negative 8, and the derivative of 5 is 0. So our answer here is 12x minus 8. And that's it. Number 19 next, I'm guessing. Yep. So for number 19, they give us h of x equals 2x to the negative 1 minus 3x to the negative 2. All right, so we want to find h double prime of x. So again, second derivative. So I'll get the first derivative. So negative 1 comes out, we get negative 2x, and now we need to subtract 1 from negative 1, so that gives me negative 2 up there. Then the negative 2 comes out, hits the negative 3, becomes a positive 6x, and then subtract 1 from that, we get negative 3. There's my first derivative. My second derivative, I do the same thing. I bring this negative 2 out. Negative 2 times negative 2 is positive 4. I subtract 1 from the power. Here I bring negative 3 out. That's going to give me negative 18. Subtract 1 from that power, I get negative 4. And just keep in mind that this really means 4 over x cubed minus 18 over x to the 4th. If I were to use a property of exponents and drop these down, the 18 would stay up top, the 4 would stay up top, but the x's would drop. So that's it. Number 21, y equals x squared minus 18x to the half. Okay. So what we're asked to do here is to find this, d2y over dx squared. So all this means, all this means is take the derivative of this y function twice. All right, so first let me find the first derivative. To do that, power rule, 2 comes down. Here we have a half, so half comes down, half of 18 is 9, and then I subtract 1 from a half. So I take 1/2, I subtract 1. That's the same as 1/2 minus 2 over 2, and that's the same as 1 minus 2 over 2, which is negative 1/2. So 1 take away a half is negative 1/2. Now I have to do it again. So I do y double prime, the derivative of 2x is just 2. And now here the power again. This negative 1/2 times negative 9 is going to give me a positive 9/2. So what I'm doing is negative 9 times negative 1/2, which is same as negative 9 over 1 times negative 1 over 2. And you just multiply straight across. Negative times negative is positive. Just leave it as a fraction, 9 over 2. Then I need to take x, and I need to take negative 1/2 and subtract 1. Which is same as negative 1/2 minus 2 over 2, which is negative 1 minus 2 over 2, which is negative 3/2. So getting a common denominator, then negative 1 minus 2, and that's negative 3 over 2. So this new power here is negative 3 halves. And that's it. All right, number 23. So for 23, they give you x squared plus 9 to the 4th, and they want to know what y double prime is. So they want us to get the derivative twice again. Now for this problem we have to use chain rule. We have to be very careful with this. We have to first realize that we have this raised to the 4th power. So we're going to bring the 4 out first. We are not going to touch the inside, and we're going to reduce the power by 1, which gives us that. Then chain rule says times the derivative of what's in here. The derivative of x squared is 2x, and then plus the derivative of 9, which is 0. So that's our derivative, our first derivative. Okay, so all I did here is move the 2x out here with the 4 and made that 8x. This is our first derivative. Now the second derivative is going to be a little complicated. The second derivative, what we need to see is that we have a product. We have multiplication here. And so if we call this function f and this entire function over here g, what we need to do is f prime times g plus g prime times f. That's our product rule. So I need to first start out by finding the derivative of this function right here. Derivative of 8x is just 8. And then I'm going to multiply that times g, which is just this function without taking any derivative at all. Then I say plus, now the derivative of g, and this is the part that's a little tricky. If we just look at this right here, and we take the derivative, we're going to have to use the chain rule. So the 3 is going to come out first. We're going to not touch the inside. We're going to reduce the power by 1. Then we're going to say times the derivative of what's inside, which is 2x again. And that, when we move this out front, we get 6x times x squared plus 9 squared. So the derivative of this is this, and that's just this part of the formula. So I'm going to just slap that right here, 6x times x squared plus 9 squared. So that takes care of g prime. And now I need to multiply that times f. So times f, which was 8x. And there's, I guess, a little bit more I can do here. I can do 8 times x squared plus 9 cubed. I can put the 8x and the 6x together. That'll give me 48x squared when I multiply those. And then I still have this x squared plus 9 squared. So there's your second derivative. That one's a little messy. All right, now let's look at number 31. They give you f of x equals x to the 4th plus 6x squared. So what we're supposed to do here is find where the function is concave up and where it's concave down, and anywhere we have inflection points. So where it's concave up, concave down, and inflection points. So when we talk about concavity of a function, we need to look at the second derivative. So let me take the first derivative. I get 4x cubed plus 12x. That's just our power rule. Take the second derivative, which is 12x squared plus 12. So just taking the power rule again on this. And now what I do is I set this second derivative equal to 0. Kind of like we did in the last section, except we're working with the second derivative instead of the first derivative. So set that to 0. And yeah, we're going to have an issue here. We're going to move the 12 to the other side, which makes it negative 12. We divide through by 12 and we get x squared is negative 1. So divide both sides by 12. And there's no way you can square a number and get a negative. So this is kind of like a problem we had in the last section. The second derivative is never 0. Okay, that's what this is saying. We have no solution here. Therefore, the second derivative is either always positive or negative. So what I'm going to do is draw a number line, and I'm just going to pick any arbitrary test point. So let's go with 0, and I'm going to plug that into the second derivative and see what I get. So here's my second derivative. Let's plug 0 in. Plug 0 in here, it goes away. I get 12, and that is a positive number. And if your second derivative is positive, that means your original function is concave up. Looks kind of like a smile. So now I can answer the questions. Where is the function concave up? Where is the function concave down? And then any inflection points. So where's it concave up? Well, everywhere. So it's always concave up. Where's it concave down? Never. And inflection points, I don't have any. Because in order to have an inflection point, we would have to have like a table here. And it would have to go from like concave up to concave down, or from concave down to concave up. We need it to switch. And since we didn't have any switching of concavity, we know that we have no inflection points. All right, that's it for that. Let's take a look at a different function that perhaps behaves a little different than that one. So number 33 is x cubed minus 4x squared and plus 5x minus 2. All right, so same questions. We want to know where it's concave up and concave down. So I take my first derivative. There's my first derivative. I take my second derivative. All right, and now I set my second derivative equal to 0. So I'm setting 6x minus 8 equal to 0. I can move the 8 to the other side, and I can divide by 6. So I get 4/3 is the point at which my second derivative is 0. So I go to a number line, go to 4/3, and pick some test points. So I'm going to pick 0, and I'm going to pick, how about 3? And I'm going to plug these into the second derivative and see if I get positive or negative answers. So if I plug 0 into the second derivative, 0 right here kills that, I get -8. That's a negative number, and that means my original function is concave down here. If I plug 3 into there, 6 times 3 is 18 minus 8, that's going to give me 10, that's a positive number, so I know my original function is concave up there. So now I can answer these questions. Where is the function concave up? Well, to the right of 4/3. So from 4/3 to infinity. Where is the function concave down? Well, to the left of 4/3. So negative infinity to 4/3. And as far as an inflection point, I do have one. I have it at x equals 4/3. So at 4/3, we go from concave down to concave up, and that means we have an inflection. Now, I'm not going to actually plug this value into the original function at this point in time. We'll do that later on. We've answered the questions that we've been asked to do here. All right, let's look at number 35. So for number 35, we have this nice polynomial here, negative x to the 4th plus 12x cubed minus 12x plus 24. Okay, first derivative, negative 4x cubed plus 36x squared minus 12. So I'm just using my power rule on this. Now I take, wait, was that x or x squared? Yeah, it's 12x. Okay, so now I'm going to take the derivative again. 3 comes out, I get negative 12x squared X comes out there, I get plus 72x, and then derivative of negative 12 is 0. So there's my derivative, my second derivative, and I'm going to set that second derivative equal to 0. So I set negative 12x squared plus 72x equal to 0. And I notice I can get a common factor out here. I'm going to pull out, let's see, I can pull an x out. I think I can also pull a number out, right? 12 goes into both of these, and I'm going to pull a negative 12 out. And if I pull negative 12 out of here, I'm going to have an x here. So this times this gives me this. And then I'm going to need a minus 6 here, because a negative times a negative will give me positive, and 12 times 6 is 72. So I already have the x right here, so I don't need an x here. So that's it. I set that to 0. I get x is 0. I set this factor equal to 0, get x is 6. So on my number line, I have two important points here, 0 and 6. I pick a test point over here like negative 1, pick a test point in here like maybe 3. Anything over here, how about 10? I take those and I plug them into the second derivative. And I figure out if it's positive or negative. So I'm plugging into here, into this right here. So let's go with negative 1. If I square negative 1, I get positive 1. But then times that gives me negative 12. If I put negative 1 right here and then times 72, I'm going to get minus 72. And that's a negative number. So I know my original function is concave down here. If I plug in 3 into this, I get 3 squared is 9. 9 times 12. So 9 times 10 is 90. 18, 108, negative 108. And then if I plug in 3 here, that's going to be like 216, I think. So plus 216. Anyway, it's going to be a positive number. Okay, this one was a negative number. This one is positive. So that means I'm concave up here. And if I plug in 10, let's see, 10 squared is 100. Then times negative 12. That's negative 1200, and then if you plug 10 in here, you're going to get like 720. This should turn out to be a negative number. So we're going to get concave down. So where is this thing concave up? Only between 0 and 6. Where is it concave down? Well, to the left of 0 and to the right of 6. So left of 0 is that, and right of 6 is that. Inflection points, I actually have two of them. X is 0, X is 6. Because at 0 you go from concave down to concave up, and at 6 you go from concave up to concave down. So anytime we have a change in concavity, we have an inflection point. All right, so number 41, let's skip 41, we're not going to do that. Let's go to number 49. Okay, I believe we're going to just put everything together now in this. We want to summarize the pertinent information obtained by applying graphing strategy to sketch this function. F of x equals x minus 2 in parentheses times x squared minus 4x minus 8. All right, so let's take care of some of the issues first that involve the derivative. The first derivative of this function. To get the first derivative, I can use the product rule because I have a product here, or I can multiply this all out. I'm going to do the product rule. So we're looking at this as f, and then that's g. So the derivative of f here, the derivative of x, which is 1, minus 0. So this is just 1, times g plus, now the derivative of g, which is 2x minus 4, times f, which is x minus 2 in parentheses. So that's my first derivative. And let me actually figure out what this is. This is x squared minus 4x minus 8. I'm going to go ahead and multiply this out. So I'm going to trust that you can do this. Foiling, you're going to get 2x squared, and then you're going to get minus 4x, then minus another 4x, so minus 8x, and then you get plus 8. So that's what happens if you multiply this out together. Now I'm going to collect all my like terms together. So I've got x squared and 2x squared, that's 3x squared. Minus 4x and minus 8x is minus 12x. And minus 8 and plus 8 is 0. So that's what I get. That's my first derivative. Now my second derivative, I may as well get it while I'm here, is the derivative of this, which is just 6x minus 12. Okay, let's talk about the first derivative. For the first derivative, if I take my first derivative and I set it to 0, that means I'm taking 3x squared minus 12x and setting it to 0. I will get a common factor of 3x to come out of that. And then I set each of those equal to 0 and I get two solutions, 0 and 4. So if I draw a number line, here's 0, here's 4, and then I pick test points. Now I'm not actually going to plug in the test points, we're just going to do it. If I plug in a test point over here, like -1, we're going to get a positive. So this function is increasing here. If we plug in a test point in here like 1, we're going to get a negative, so my original function is decreasing. And if we plug in a test point over here like 5, it's going to increase. Now, again, I'm not doing that. You could plug in 5, you could plug in, let's say 1, you could plug in like -1 yourself and see that that's what would happen. Okay, so we're going to just hang on to that information. We'll come back to it in a second. Now let's take a look at the second derivative. Where is that 0? So the second derivative is 6x minus 12. I want to know where that's 0. So that's 6x equals 12, moving the 12 to the other side. So x is 2. So I only have one result there. So I have, if I draw a number line 2, I have to pick two test points, here and here. So this should be pretty straightforward. Here's 0, here's let's say 3. Plug those into the second derivative. So plug them into here. So if I plug in 0 into this, I'm going to get a negative number, which means my function is concave down. Remember, second derivative means we're looking at concavity. If you plug in 3, you'll get a positive number. That means we're concave up. All right, now with this information, we should be able to draw a pretty good little graph of this function. All right, so here's what I'm going to do. I'm going to go and try and graph this, and I'm going to only plug in these points. The ones from the first derivative, where I got 0 and 4, I'm going to grab those, and then when I set my second derivative equal to 0, 2, I'm going to take those 3 points and I'm going to plug them into the original function. So I'm going to find f of 0, f of 4, and f of 2. And those are going into my original function. This is so I can get some actual points to plot. So at 0, if I plug 0 into this, let's see what I get. And I need to leave this information up on the board so I can refer back to it, but I can erase this. Okay, so we don't need any of that. We just need these two tables here. So if I plug in 0 up there, I'm going to get 0 minus 2, 0 squared minus 4 times 0 minus 8. So 0 take away 2 is -2, times 0, 0, this is just -8 in there. And -2 times -8 is 16. So at 0, I go up to 16, and I have a point on my graph. Now at 4, I need to plug 4 in there. It'll be 4 minus 2, and then 4 squared is 16 minus 4 times 4, which is another 16, and then minus 8. So here you get 4 minus 2 is 2 times, the 16s cancel, so you just get negative 8. So I should get negative 16. That's what's happening at 4. So here's 4. And I'm down here at negative 16. And then at 2, when we plug 2 in there, notice what happens. 2 minus 2, then 2 squared is 4 minus 8 minus 8. So I just plugged in 2 here, 2 here, 2 there. And this really didn't matter because these two together are 0, and 0 times anything is 0. So we get 0 there. So at 2, my graph is 0. All right. Now, let's try and figure out from this table what's going on. To the left of 0, my function needs to be going up. So to the left of 0, my function needs to be increasing and getting to this point. At that point, I go up and then down. So I should have a highest point there, right? And it should also look like a frown until I get to 2. So it's got to be, to left 2, it's got to look like a frown, right? And it's got to be increasing here. Got to go to the top, right? And then it's got to start going down. See, between 0 and 4, it goes down. So this has got to start coming down, and it's still got to look like a frown. But once I get to 2, it's got to start looking like a smile. All right? So it's going to look like a smile now, which is going to be like this part right here, right? This is going to go down like that. It's going to go down, then back up, but it's going to look like a frown, a smile the whole time. So it's going to go down and then come back up like that. There we go, like this. So that is the graph. So that's number 49. I think what I'm going to do is I think in class I'm going to do 51, 53, and 55. I'll do that together with you in class. I want to skip over to 87. Get to a word problem. I might show you all kind of a different way of doing this because this gets a little bit weird. I might show you a little bit different technique for that in class. It just takes a little more time, so I'm not sure if I want to do it. Okay, so you can try those others on your own without me doing them in class. You can try them for yourself, but I will do 51 through 55 in class. All right, number 87. So talks about a marketing research department. They come up with this price demand equation, and then from that they're able to determine what their revenue function is. So the revenue function, they give it to you right here, is 1296x minus 0.12x cubed. They say that this is good for 0 to 80, for any x value 0 to 80. So it says find the local extrema of the function, the revenue function, and on which intervals the graph of the revenue function is concave up and concave down. So we're basically going to be following the same procedure we did earlier to try and find where this thing is increasing, decreasing, concave up and concave down. All right, let's do it. I'm going to need both the first and second derivatives for this. So my r prime of x, my first derivative, I take derivative of 1296x, which is just 1296. 1296. Okay, minus, now the 3 here needs to come down. So 3 times that's going to be 0.36. 0.36x squared. That's my first derivative. Let's just get my second derivative while I'm here. Second derivative, well, the derivative of a constant is 0. And then I'm going to do the same thing here. I'm going to bring the 2 down. That was negative, so it's negative 0.72x. Now, to figure out where it's going up and down, I'm going to take my first derivative, set it to 0. So I'm going to take 1296 minus 0.36x squared, set it to 0. I'm going to move this to the other side. Since it's negative, I'm going to make it go to the other side, and that'll make it positive. I'm going to divide both sides by 0.36. 0.36. So 1296 divided by 0.36. I get 3600 is x squared. And then I'm going to take the square root on both sides. So I get square root here, square root here. I have to do plus or minus. So I should get, let's see here, 60. Yeah, I don't know why I was second guessing myself there. X is plus or minus 60. So normally what I would do is I would just do a number line. I would do plus 60 minus 60, right? Like that. And then I pick test points. Here's the deal though. Our x can only be between 0 and 80. So I really don't need to even look at this region. I don't even care about that. But here I should probably look. I should probably pick something in here, 0, and then maybe over here let's pick, I don't know, 70. And let's plug these points into the derivative. So if I take 0 and I plug 0 into the first derivative, 0 right there, I'm going to get a positive number, which means my original function, my revenue function, must be going up here. And then if I plug in 70 into this, you'll just have to get your calculator out and do this computation. Plug in 70, you're going to get a negative, which means my revenue function is decreasing there. Right, so what I have is well, do they ask for local extreme? Yeah, they want the local extreme of the function. I have a local max at x equals 60 because it goes up and then down. That happens at 60. And that means if I take my revenue function, my original revenue function, and plug 60 into it. So if I plug 60 into this, I'm going to actually figure out what that maximum revenue was. 1296 times 60 minus 0.12 times 60 cubed. Make sure I type that in all right. It's 51,840. So I am going to have a maximum revenue of $51,840, and it happens when x is 60. Now in the word problem, x is the this is a computer company. X is the demand per week. How many computers per week there's a demand for. So we have a demand of 60 computers a week. Our maximum revenue is, we will have a maximum revenue of $51,840. Anything over that, anything bigger than 60, so anything from 60 to 80, we're going to have less revenue. Anything less than 60, we're going to have less revenue. All right, and then the second part of this is to figure out where it's concave up and concave down. So what I'm going to do is I'm going to take my second derivative, set it to 0, which means I take negative 0.72x, set it equal to 0. And this is pretty clean because I can just divide out negative 0.72 on both sides. And this goes away, I get x equals 0. So I only have one critical number here. It's going to happen at 0. And so I'm supposed to pick test points here and here. Again, I'm not going to look over here because my x has to be bigger than 0. So no need to look over there. So I just pick a test point here like 1. And I plug that into the second derivative. So if I plug 1 in right here, I'm going to get a negative number, which means my original revenue function is concave down there. So it asks on which intervals of the graph is the revenue function concave up or concave down? Well, you would say here, this graph is, the revenue is concave down on the entire interval from 0 to 80. So the whole time we're concave down. So this graph kind of looks like this. And then it's never concave up and never concave up. All right. So that's it. Again, I did skip 83 and 85 I'm not going to ask you anything like that on a test. I'll be more like 87. So I will do those other graphing problems in class, and that should wrap up the homework for this section 12.2.